Thank you. Thank you very much. It's actually quite an honor to be here. So, and as I just told Benjamin, I feared I would stand here without a working laptop. I had a little mishap with a core dump that exceeded the size of my disk. Somehow it miraculously recovered. Anyway, so I'd like to say a few things. I'm not even going to slides for that. To use slides for that about what AD-Link is, what AD-Link does, why there is a French address in the on the slide, and why my name looks French, but it's not actually French, but Dutch. So AD-Link is a Taiwanese company, originally specializing in measurement equipment and then branching out into industrial PCs. Now it makes a ton of things. And a ton of the things that we make are very suitable for the IoT business. And so a natural next step is to say, well, what can we do in the software platform that you need for the IoT? This is where we come in. I used to work for a different company called PrismTech, which was bought up by AD-Link. And there we did DDS. Now, the PrismTech has an office in Paris, and that's where the Advanced Technology Office is, primarily. I'm also a member of it, but I live and work in the Netherlands, but I now spend a decent deal of time in Taipei at headquarters. Hence the little bit of a mix-up of things. Now, we are not a really big company. We're not really small either. It's like 2,000 people, 350, 370 million US dollars a year revenue, something like that. So we can take some risks in where we invest. We can take a little bit of a risk in deciding to invest in open source software, even though it's not going to be very much appreciated by the commercial people that used to make their commissions of selling DDS. It's also interesting to see how the different vendors of DDS systems respond to such a thing. Okay, and so the name really is Dutch. Don't worry about it. Most people assume it's French, but it's simply one Dutch guy out of 11 sons, I think, 200 years ago, that decided to add son to his name to distinguish himself from his siblings. I guess that's a dominant gene. So firstly, I'm going to repeat everything that's been said before, because it turns out that we're all totally in agreement. A lot has been said about the importance of data in IoT systems, a lot of how data is the most valuable asset that a lot of organizations have these days, how cities are looking to exploit it. Now, the concept of monetizing the data sort of scares me. I'm not, even though we are also working towards proper security for the data, and even though everybody talks about it, I still have read a few things too many of mishaps with security. So it really scares me. And the other reason it scares me is because it reminds me of a term called valorization. I just Googled it. It's actually an English word too. According to Wikipedia, it's the value creation in Marxism out of labor. So that's not something that I feel very comfortable with. But the other reason is it's in the Dutch government-funded research. You always had to valorize your research, and you had to prove upfront how much money it would ultimately bring the state, or bring maybe not the state, but just the general economy. And of course, having to do that killed the effectiveness of the research program. So the focus on monetizing data kind of worries me, but a focus on exploiting the data to make your system processes run better, well, that's something I can totally support. And so thankfully, we are more focused on the industrial IoT than on the consumer side of the IoT. And in the industrial side of the IoT, as has been mentioned here earlier today, there is a lot of concern about security of data, about provenance of the data, about the compliancy with all kinds of regulations. So basically, most companies are not trying, and industries are not trying to make direct money out of the data they have. They would rather try to use it to optimize their processes. So that's fine. That's cool. So there are a number of problems that have been mentioned, and Ian spoke this morning, this second one, I think, about MQTT, and MQTT is probably the best known publish-subscribe system in the world. And the whole point of publish-subscribe is that you don't want to know where data has to go to. You don't want to be dealing in addresses all the time. You want the system to work that out for itself, so you subscribe to something you care about and you publish, and somehow the middleware will figure out what has to go where. Now you can scale this from a single computer to a network, a local area network. You can scale it to a factory size or to all the way up to the cloud. The details, of course, of how you do publish-subscribe, what actually you subscribe to, what you do with the data, to what extent you model the data in your system, on the list goes. Those, of course, differ completely between different publish-subscribe systems. And one of the big differences between DDS and MQTT is that DDS comes from a world in which peer-to-peer data sharing is by far the most important thing, whereas MQTT has a tradition of saying there has to be a broker, and each client knows the broker, sends the data to the broker, and it will work. I'm not sure if there are any other alternatives within MQTT, but in any case, that's the model that everybody uses and thinks of. But in DDS, the basic premise is that you connect, you directly transmit the data from all the publishers to all the subscribers to the data. And so and that's reasonable in the typical traditional environment of DDS, which is a local area network. So you can use UDP, you can use multicast, you can map your data over multiple multicast groups, and so you can make sure that the big data flows actually only arrive at the nodes that actually care about it. And then the hardware does essentially supports the publish-subscribe mechanism. And then you use unicast, of course, if there is only one that cares about it. But at the same time, if you want to scale up, peer-to-peer is never going to scale to billions of nodes. Well, potentially it would, but if there can be a billion subscribers, it will never fit. So you also need a brokered architecture. And some of the trade-offs and some of the design decisions that were made way back when in what is now DDS really facilitate that freedom. And when I say way back when, it's well, 1984 basically. So I was only a kid when my father invented it. Another essential thing, and I think this is one that's not sufficiently highlighted in most middlewares, is the value of temporal decoupling. There are many aspects, or at least several aspects of that matter. One is that you may not know when a subscriber comes online. But when a subscriber comes online, you may actually have a good reason to want to get the current state of the system. So that's one form of historical data, of durable data, and of temporal decoupling. Another is that you may have publishers that produce a too high data rate for the subscriber to process it, in which case you would overwhelm the subscribers. It could also be the network. In that case, you would actually want to have the freedom to drop data. It's not strictly perhaps temporal decoupling, but good enough, close enough. And if you want to be able to drop data automatically, if the data rate at the publication is too high, then it makes more. You need to know more about the data than simply say it's a blob. So you need an underlying notion of what your data model is and what the meaning of data is, and also in a consequence, you need to think about how you delete data. So those are aspects that turn up in DDS that don't really have a big place in the other data sharing middlewares. Well, security is obvious. And this interoperability, I mean, goes without saying, right? And there is nothing special that we can do here. DDS is already a standard. DDS has been a standard since 2004. There is an interoperability protocol. It was standardized in 2006 or something like that. There are multiple vendors. They can interoperate via the interoperability protocol. So basically, interoperability amongst DDS systems is a solved problem. Interoperability to other middlewares to other platforms is a matter of using gateways. There's not going to be a way around that. So here, actually, this is something I wanted to remark on. You see the big advantage of being a first mover in open source. MQTT came much later, in 1999 versus 1984, but quite soon decided to go completely open. And in consequence, whereas DDS was kept closed for decades almost by the industry that considered it a strategic asset, and therefore could absolutely under no circumstances fall in the hands of a competitor. And so here we stand, MQTT, basically a youngster to me, on the left side of the diagram as the most used technology in Eclipse IoT survey, and DDS, well, it makes it into the graph, but on the far right edge, at I think 4.7%. So with this number of people around, and about 1/3 having affinity or having worked with MQTT, and considering those ratios, probably I'm the only one here who knows DDS. Is that true? Good. I can still do my math. So, Cyclone ETS is the Eclipse project. The process got started about a year ago. It took a while. We have this relatively well-known implementation OpenSplice within the company. But it turns out that it's a rather large amount of code, and getting it through the IP verification process, which is one of, it's one of the fact that our Eclipse organization does that is one of the reasons that it's very valuable for us to participate in the Eclipse ecosystem. The fact that you can count on something about IP rights. And so in the end, we switched to a new development that we were doing. And it's smaller, and therefore much easier to get the IP validated. And it's also, as a side benefit, it's much easier for people to contribute to. The downside, of course, is it's less mature and there is less functionality at this point in time. And we're working on it, and we hope that others in the community eventually will join in and make sure that it actually is fully featured. But it's based on the DDS technology from DDS standard from the OMG. So where do we see DDS being used? There are a bunch of examples here. I could list many more. It's been around for a long time, and there's multiple vendors, and there's tons and tons and tons of systems that use it. So one of them is smart grids, where you need to keep synchronized the phase throughout the network. You need to distribute information for that. You need to monitor the behavior, the loads in the system, all kinds of things. And one energy corporation in America, Duke Energy, used DDS to do that. There is another case of power generation where DDS is used. I mean, it's used in the Grand Coulee Dam, for example, in Northwest America, which is probably the largest hydropower plant in America. And there DDS is used for the entire control and monitoring system, which means, I mean, loads and loads and loads of sensors, but still in a confined area. Smart greenhouses, it gets used. Smart farming in general. Greenhouses is this picture probably comes from a company in the Netherlands that uses it for building management and monitoring the temperature, the humidity, everything. There are also others. There was a time when I joined PrisonTech that we were working with John Deere to get automated vehicles in the field where the harvester would be driven through the field, and the collecting cars, tractor plus trailer, would drive automatically next to the harvester. And the interaction between the two went over DDS. So it gets used in farming, in greenhouses. NASA uses it in various systems. This picture and the text, I realized, don't make sense together. I'm sorry. That picture is not a space shuttle. And the shuttle is no longer there, but shuttle service ended in 2011, so it's possible that DDS was used in shuttle launch system, but it can also have been used in another Kennedy Space System. Kennedy Space Center system, for sure. But there is also DDS running in a Mars Pathfinder robot and other NASA programs. As you can see, the data rates you're talking about here can be quite high, hundreds of thousands of messages per second, and some really low latency stuff as well. Air traffic control, the pan-European air traffic control system uses DDS between data centers. Of course, this being Europe, the system has to be developed by 2 independent consortia in 2 different countries. So there is one consortium is Thales Celex, French, Italian, and the other is Spanish and something. I don't know what the Spanish guys are using, but they're using DDS in one form, way or another. But the French-Italian one is using DDS inside the flight data center, and so pushing all the flight plans and sharing the flight plans, updating all the flight plans via DDS. That's quite a critical, safety-critical application. Others are, in aviation, are like full flight simulators, where the simulation is controlled and all the interaction between the avionics boxes is done over DDS. And so you have like a 16 millisecond round-trip latency between touching your stick and the output updating, and goes through I don't know how many stages, and that's hard real-time. SCADA, this one's quite cool. The European Extremely Large Telescope, which uses adaptive optics. It's in somewhere in Chile, in the desert. So the control system, with adaptive optics, you send a very powerful laser beam into the sky. And then you look at it through your telescope, and you adjust the mirrors, all the tiny mirrors that together make up your telescope, to create a perfect picture, or as perfect as you can get. And of course, the atmosphere changes all the time. And so you have to have this real-time control loop adjusting, 100,000 mirrors at about 100 hertz to actually make this work. So that's built using DDS. Medical devices, it just goes on. Robotics is a little bit different. Of course, it gets used in robotics, so you could have guessed that. But the particular thing about robotics here is that there is this open source project, ROS, the Robot Operating System. And they've not so long ago released ROS 2, a major update over ROS 1. ROS 1 used their own bespoke communication system over TCP. They needed to broker, blah, blah. And they were not quite happy with the properties they got from that. They were not happy with the lack of real-time properties, the way faults would be handled. I don't know, there were all kinds of considerations. And so they looked around and they said, you know what, we don't actually need to do our middleware anymore. We could just slot in DDS, and it ticks all our boxes. So they did just that. And now they did not say build your robot on top of DDS straight, but they said build your robot on top of our ROS API, just like you used to do, and keep using the ecosystem that we have and that you contribute to for all kinds of things that you need in robots, like path planning or what's it called, robot arm control. And there is a middleware layer in between ROS and the DDS middleware that adapts to the different DDS flavors that they can find, or anything else that you can do. And so there is a ROS middleware layer for OpenSplice and for RTI and for fast RTPS, and for Cyclone there is a partial one at the moment. And there is a reason why it's partial, and that's that there is still a tiny little bit missing in functionality to make it full, and I'm currently working on that. So you could have guessed, or I basically said, all these systems are using DDS for one reason only, and that's that it provides a very good set of abstractions that fit the nature of these real-time control systems, these not just real-time, also fault-tolerant control systems and long-lived ones, with what you can actually achieve and the possibilities of the current hardware. And the really surprising thing is that this was true 30 years ago, and it's true today. So we must have really, or we, I wasn't part of it back then, but it must have really, it really found an excellent combination of features and abstractions for this kind of systems. And it doesn't mean it's good for every kind of system, but as soon as you get into this combination of low latency and fault tolerance, distributed nature, it really helps. Yeah, well, it's nice, right? Universal glue. So the what is then? You could argue, or you could ask the question, what is DDS? And the DDS gives you a programming model that's based around a shared data space, where applications simply read data from the data space or write data into the data space, update the data space. They do so asynchronously. The idea is that applications synchronize as little as they can get away with in order to maximize the benefits that you get from the decoupling that this model allows. And some of the detailed properties of the data space and detailed properties of the operations give you the spatial and temporal decoupling, the spatial one across the network, the temporal one that you can wait and read much later, or that you can read at a lower rate than you write. The topics in DDS are, well, you have a name, of course, it identifies the topic. But it also has a type. So DDS gives you a strongly typed shared data space, much unlike most systems. And it has QoS settings, quality of service settings, that are quite extensive. There are about 25 QoS settings, different QoS settings, and they all deal with different aspects of the trade-offs that you have to make. Like you may be able to tolerate, you may require really high throughput for something. But then if you run really high throughput, you will have to have some tolerance for latency. It's just the nature of the beast. And so you're allowed to say, okay, fine, I'm accepting that if you take a little bit of time in delivering this data. So I'm cool with this data taking 100 milliseconds to reach the destination. But this other one, I need to be sent as fast as possible. Similarly, you can prioritize data. You can specify what data should be retained by the data space independent of the processes until somebody comes along and needs it. And that's the durability constraint. You can then also configure when exactly that data may be deleted from the space, and so on and so forth. So it gives you a very fine-grained control over the various trade-offs that you have to make. Obviously, it has dynamic discovery. I mentioned that before. And one of the really nice things, and this is really because of a peer-to-peer nature, but it's not only because of peer-to-peer nature, because you can do it also when there is a broker, but because it's fundamentally based around replication of data at the subscriber sites to give the lowest possible read access to the subscribers. Well, basically you can kill any node if you have multiple nodes, and the data will still be around. As the data is the most important bit in your system, and all the state is stored in there, you can just restart the application on some other node, and the system will continue. I mean, if you want to, I could probably do a demo. But and so this taking redundancy, taking replication, in combination with asynchronicity as the basic design philosophy, essentially gives you the ability to build a system without a single point of failure. Now, of course, we want to be able to scale out to huge systems as well, where we need brokers. So then you need to have multiple copies of the programs running, and you need to do all kinds of tricks to make sure that they behave nicely together. And you're squarely back in the old problem of writing fault-tolerant software with failover and everything. But as long as you can have a fully symmetric configuration, you can basically do magic with this. Oh, right, yeah. And so, as I mentioned, there is support for multiple protocols, and you can use the low-level protocol attributes to optimize your data flows. Here it only mentions UDP and TCP, but there is no reason it would ever be restricted to IP only. The basic protocols that we use rely on an unreliable datagram service like UDP. So give us anything, any unreliable radio link, and we can build a system. Any unreliable satellite link, we can build a system. The other fairly often mentioned point is that it's very important to be independent of the platform. Now, I know that platforms mean many different things, but at least in terms of operating systems and hardware, basically there is most DDS implementations out there support pretty much everything. It comes from a real-time world. So running on Linux is a luxury, but you have to be able to run on Wind River or on QNX or on FreeRTOS even. Again, that's DDS systems in general. Cyclone DDS, currently I only bother with macOS, Linux, and Windows. Usually in that order because I have a Mac, so it's easiest in that order. Similarly for programming languages that get supported. Here too, Cyclone is a little bit behind because like today there is only a C API, which you can call from C++ or you can call it from any other language. And so we have a small Python binding and we have a small OCaml binding, but the other languages have all been, well, firstly the rest will be added as needed. And obviously Java is going to be added, and obviously C++ is going to be added. Another one that might actually be added is, not on this list, is Ada 2012. Just because I kind of care about high integrity software. Haskell, I once did a proof of concept, and it works beautifully for OpenSplice, and so it's a matter of translating it. And it doesn't really matter what language you write the application in, or what platform you run on, because the data types are known to the system, and so it can do all the conversions from the application language, from what is natural in the application language to something serialized on the wire, and back on the other side to whatever happens to be good on the other side. Given all that, you might expect that it's a lot of work to write applications that use it. And if you look at the original OMG C API, you most definitely would have been right. But that's because the OMG made the unfortunate decision to specify the interface in their interface definition language, and then simply convert that into C, or convert it into C++ and say, so, fine, we now have an API. The cool thing about it is, of course, that you can integrate very elegantly with Corba, which is a very important point for the OMG, I guess, having been the inventors of Corba. But most of the world doesn't care about Corba anymore. And so finally, a couple of years ago, a new C++ API was introduced, a new Java API was introduced, and they actually use the features of the languages. So suddenly in C++, you can actually use templates instead of having code generated and in crazy ways. The C API was never really replaced, so we said ourselves, we're not going to even bother with implementing the old C API. And so Cyclone has a new C API that was just written to be a C API. And so it's actually roughly as much code to write as the Python API. Python obviously also did not suffer from being converted from IDL. So it's very straightforward. C++, as you can see, this is the new API. I have a colleague working on it right now to add this to Cyclone. So it should be there in, well, a couple of weeks or so. Scala, it's the same thing again, right? I could add Java, but it would be yet another copy of the same. Haskell really is a little bit different. But I decided not to copy paste it into here, because who cares about Haskell? So what are the things that we are looking towards doing with this right now? Well, some things that are really high on our priority list are not even in the roadmap. They're so high in the priority list, they don't even need to be in a roadmap, because they should have been here already. One of them is C++ support. One of them is Java support. Getting rid of the requirement that you define your topic types in IDL will really make life easier in integrating with others. Similarly, eliminating the dependence on Corbas CDR, common data representation, I think it's called, serialization format, will also help. So it will replace the kind of enforced use of IDL and CDR by allowing taking an anything goes attitude and allowing any kind of serialization to be plugged in. And that means that once that's done, well, if you want to take JSON as the native format, then you can. Of course, if you take JSON, then suddenly there are less guarantees about what fields will be available, and that can be a problem in defining your caches at the subscriber sides. But okay, fine, that's another problem. 25 odd QoSs is a lot, and we've learned over the years that people find it really hard to figure out what to do, what to set, which to ignore, where to start. And usually these customers that start using it, or the new users, set all kinds of options that don't need to be set, and they set all kinds of weird things. I understand why, because it's just too much. So have an easier way of specifying roughly what category you want is something pretty high on the list too. A lot of the data has kind of a predictable quality, like in MQTT you have QoS 0, 1, or 2. I mean, people can, without ever having dealt with anything, people can remember one is better than 0, or 2 gives you more guarantees than 1. Well, we would like to say you typically have state data in the system, you have telemetry data in the system, you have events occurring. And for example, an event, you just have to make sure that every event that happens gets transported to the other end. But if it's state, you can just say, well, all I care about is the current state of the system. So that maps to all kinds of settings for all those individual QoS settings of DDS. But you won't have to deal with them anymore. Some tooling, of course, is nice. Time-sensitive networking is really growing in popularity in the industrial control world. We will add support for that. It's still in its infancy. The TSN hardware is like available now in small quantities. But being part of a hardware company makes it that makes switches and that makes computers, makes it kind of easy to get access to early samples and integrate that. Raw Ethernet support is already done. And as I mentioned, ROS2, well, obviously the RMW layer of Cyclone needs to be completed before it can become the default implementation of ROS2. And whether it will become the default implementation of ROS2 or not is kind of up to us. We will have to do a better job than the others for that to happen, but that's the aim. DDS, the OMG has security, is an OMG standard that was done over a couple of years with a lot of input from a lot of very security sensitive people in various governments. So now that US DoD has approved it, the English Ministry of Defense is happy with it, there is a reasonable chance that it's actually a well thought out security model. That work to implement that is currently on the way, and so that will show up in the near future in Cyclone as well. So then, of course, the question is this all you do? You call yourself advanced technology, right? So no. There is FogOS, which was mentioned before. I'm curious. Would be interesting to know how exactly it relates to IO fog. There is a lot of overlap there. But the feeling is that we need a unifying model for covering everything from the small things to the cloud and all the stages in between. treating it as or a cloud server is different from an edge server is not going to get us anywhere. And so the Foggle5, FogOS stack unifies all that and allows you to deploy applications. You specify your requirements, and then we map it onto the available hardware. And it builds on, not quite on DDS. I mean, you would have expected that from us, but it builds on named data networking, which is a next generation internet activity, where it's recognized that actually now we have all these, and we see it in practice, right? So many people are starting to use publish-subscribe systems because they say, but I don't care about the location of the machine. I don't care about the address of the machine. What I care about is the data. Well, there are very interesting developments in various places sponsored by the National Science Foundation and other things to look at future internet technologies to eliminate the entire notion of IP addresses and say machines don't really need to be addressable, but it's only about the content. And as you start thinking about it and you start looking what you could do if you were to completely abolish machine addresses, then of course your routers would have to work differently and your gateways would have to, everything would have to go differently. But a lot of that is happening. When that ever is going to become the standard for internet access, well, IPv6 rollout is still not going so super smooth. So a changeover to a completely different system, even if it has some backwards compatibility, might take some time. But still, it's a very interesting direction to be looking in. And if you take named data networking as a basis, then the whole concept of how you build your data distribution systems, your data retention systems, how you do the security, everything starts changing. And so FogOS ultimately looks towards that future and says, how could we do it if only we had that? And therefore, it doesn't use, it preferably doesn't use DDS, but uses another protocol, Zeno, that we did. And it has a really nice distributed key value store on top of it that's designed to have a concept of ownership of data, where a physical node owns some data, or a group of nodes owns some data, and they actually keep all that data locally, but you can actually subscribe and get any data in the system that you like, and it ends up in a fixed size cache, so that you could actually have a very large system with fairly small nodes and be able to access any data that you need. And then obviously the agent, any distributed system that doesn't have an agent is kind of broken. You need the agent to do all the things that you postulate are important. So, well, this is what I mentioned. We're way out there on the right. And we're not really happy with that. We want to provide some real competition to MQTT. So this is the picture we are aiming for. Have DDS sit there next to MQTT at a similar height. It's going to take some effort, for sure. I hope that I have given you some sense that DDS has very unique values that might be very useful to you in systems, and that we can make this happen together. And obviously, given that FogOS is an Eclipse project, we also strongly desire to work together with everybody that finds it interesting to develop that and introduce it or create it as a really standard platform for computing. So these are some links. And with that, thank you very much. And not too many questions, I hope. Yeah.
So one of the reasons, I think, well, there are several reasons why MQTT is popular. I think one of them is that it's easy to get started and to use. One of the specification at the moment still is not over 100 pages. Well, it's about 100 pages. So even if you had no implementations, available, no standard implementations, you could think, oh, well, I could write an implementation in a short period of time. And the concepts are quite simple. So DDS is very capable. The concepts are thorough and quite complicated. So to achieve that goal means having probably standardized implementations which make it easy to use and get started. And my second thought is maybe it isn't even the right thing to aim for that amount of use. Because if we think of safety critical software with all those reliability guarantees, then that's a market which is very important, but isn't a wide market. And so maybe there are places to use MQTT and DDS has a very important place, but it isn't as widely used or a marketplace as MQTT.
Thank you. Those are very fair points. The aim is therefore also not to overtake MQTT. It's also only mindshare rate. It's not you always have to use the best tool for the job, and I totally agree. Sometimes MQTT is by far the best tool. No. I mean, it's all the things that there are so many considerations that go into a decision. What is the best tool for the job, right? So if my boss tells me I have to interface with AWS, I better start looking at what AWS is happy to take or to accept data in. MQTT is not a problem. If I now say, but I would like to give you DDS data, then they say, well, sorry, no go. So that's also a consideration that plays a role. And I totally agree that there is a huge difference in complexity of the mental model of the APIs. Now, the APIs can be, perhaps something can be done about it. The mental model, perhaps something can be made a little bit more manageable, but ultimately, yes, you're talking about a different kind of system. And so they will have their specific uses. And we shouldn't fight each other in that sense. But if we could get a little bit more mindshare than 4.7%, it would be kind of nice.
Yes, I don't think it's a fight. DDS does much more in many cases.
Yeah. Any other questions? Doesn't seem to be. Either you're all asleep or I was so clear. See, I knew. Couldn't be the case.
Well, just to clarify, probably like as you're kind of pushing DDS, do you see specific like domains or use cases that DDS like completely should be something that you should consider relative to, let's say, MQTT or something else, right?
The old traditional niche, real-time fault-tolerant control systems. That's where what it was invented for originally, and that's where it still outclasses everything else. But there is a whole class of domains in which it becomes a very interesting platform to use. Maybe not as clearly better than all the others, but possibly really, really interesting. No, actually, I'm. It's a very good point. Actually, I tend to say real-time is just following the traditional strict definition. It means predictable upper bound to the time it takes for something to happen. In practice, of course, I know people say, real-time must be real fast. Typical, like if I run a simple latency test within my laptop, typical numbers are like 20 microseconds or something like that between two processes. So that counts as reasonably fast. And that's Mac OS. So if you take Linux, it's 10 probably. But
did Robot OS use an off-the-shelf version of DDS, or did they write their own?
They use their default implementation is fast RTPS, which is fast RTPS, which is not actually a full DDS implementation. It's an implementation of the networking protocol of DDS, but that covers so much that you can easily put it underneath ROS2. So they simply use that. It's available in open source. The other one that they can use is OpenSplice, which there is a community edition version of OpenSplice, which is just a copy of a certain version of the code on GitHub. This is one of the things that the means through which we really learned the hard way that doing open source is more than taking source code and dumping it on the web. And they also have a connector for RTI's commercial product. But they did not develop their own.